what I have is something called Jupyter. So if you go to Anaconda Python, if you select Anaconda Python, there's a Anaconda distribution of Python. You can install this, and once you install this, you can run Jupyter, this Jupyter notebook. And when you first run it, you're going to see this page opening up. So either your Chrome browser or Firefox or whatever that's your default browser will be opened, and it will show this page. And what you do is you go to New and select Python 3, and it's going to open up these Python notebooks. And I have here one of the Python notebooks opened. And I know that most of you have taken Engineering 120 with Python, right? How many of you took Engineering 120? How many of you didn't take Engineering 120? You didn't take it yet?
It was with MATLAB.
Oh, okay. Some people got it with MATLAB. Okay. So, but assuming that most people have seen Python, in Python, the original language itself is not that powerful, but it has so many different packages you can load into Python that makes the Python very powerful for many things. So here what I'm going to do is I'm going to open up the NumPy package and the Pandas package. Pandas is it's a package to handle data, okay? And the reason I'm going to use Pandas is because I can read a CSV file. CSV is like an Excel file. Okay, so in Excel, you can take any Excel data sheet and save it as a CSV format. And then from Pandas, you can read it into a Python object. Okay, so I'm assigning df to be that data frame. I already ran this. And by the way, this data set is, I got it from Kaggle. It says this data is for used car sales and total of 160,000 sales records over a period of 20 months in 2019 and 2020, something, okay? So that's the data, and once I loaded them up, I can look at what's in there. So I can look at this. So it has many columns. So it's some zip codes, mileage, price sold, make and model, and different things. Now in this data set, I'm interested in just the distribution of the price sold. How's that? Okay, so let's think about the distribution of the price sold. And we're going to select only those that are sold in 2020. Okay, so I'm going to say cars 2020 equals to data frame, and I'm going to select the ones that says years old. See this years old column? If this years old, no, not years sold, sorry, it's not years old, it's year sold is equal to 2020. So just looking at the cars that were sold in 2020, if the years sold is 2020, these are selected. So internally what happens is that if this value is indeed 2020, it gives you the value of true. And then when that true is fed into the data frame again, then that part of the data frame is selected, okay? So I'm going to do this. Now let's see what's in cars 2020. Head just prints out the first 5 occurrences. And you can see that years old is oldest, okay? And, you know, maybe the mileage, if it's too new, it might be kind of expensive. Okay, let's also change that as well. So we're going to select cars 2020 equals to cars 2020, but this time I'm going to select cars 2020 with the value of mileage has to be under 50,000 miles. Let's try that. On the other hand, if it's too new, I don't like it. Let's just go for the old cars. I'll go for 10,000 miles or more, or 20,000 miles or more. Okay, how's that? Okay, so let's try this one. And then if I look at cars 2020, does it have a shape? Oh, it does. Okay. So what I just did is what's called the tab completion. If you're not sure if, so let me first say this. If you look at the type of cars 2020, it's what's called the pandas data frame type. Now, if you have an object, they come with various internalized functions. Those are called methods. So if I want to know all the methods that are available for cars 2020, I can use dir, and it gives you all these functions you can have. You can make it reindex, you can rename it, you can replace something, resample. There's so many things you can do with this. And among them, what I want to use is cars 2020, and I wanted to know the shape of this thing. So I put dot with sh, and then I typed tab. If I press the tab, what it does is it shows me all the methods that's available, or internal variables that are available with that begins with sh. And the thing I had in mind was the shape. So I'm going to select that and then shift enter. Oh, by the way, I forgot to say, if you just do enter, it doesn't execute. In Jupyter Notebook, you have to do shift enter to execute. Okay, so what does this say? It says there are 40,464 cars that are selected from a record of 160K cars, okay? So we're now going to assume that that's our population, all right? So let's look at the histogram of the, let's generate some histogram to see the price range. So I'm going to say cars 2020. I'm going to pick up the prices. Price, I think it's called price sold. Okay, so price sold. And then I'm going to generate a histogram with bins, maybe 30 bins or something like that. And it's going to give me this picture. Okay. So some cars are very expensive. It's going to 40,000 range. You know, I don't like that. Let's do a cutoff. Maybe I want something that's between under $50,000. Okay, so let's just select those again. Cars 2020 equals to cars 2020. Cars 2020. No, not cars 2020. And I want the price sold to be less than 50,000. Okay, and then now let's copy this thing here and then see if the histogram looks better. Okay, that's slightly better. Okay, but still, it's not a bell curve. Some cars are very expensive. That's what we see. Okay, so you start from here and then goes like that. Okay. All right. So now let's try to find the average. So to do that, I want to convert the prices into a NumPy. So let's do this. Prices equal to NumPy array. Now the reason I'm converting is because different objects have different methods. So I want to use some functionality of the NumPy now. So NumPy array will be generated from the cars 2020, and then I'm only looking at the price sold column. Okay, so the prices of each car that was sold is now going to be stored into prices. And I can now calculate the average. How do you calculate the average? You have to add them up and divide it by the size of the number of elements in there. So that's called length, L-E-N, of prices. If you divide, let's just call this the average. Average is this. And then how do you get the variance? Variance would be equal to, you first want to add up the difference between each individual price minus the average. And you square that. That's how you square in Python. And then you divide this again by the length of prices. Okay, so by doing this, you can find the average and variance and standard deviation. Standard deviation would be the square root of variance. Okay. So after computing this, let's print those out. Average, variance, standard deviation. Okay, so these are the values that we have. We see that the average value of car price is $8,867, and the standard deviation is $8,621. Okay. You can also do internal functions. So if you do prices, now there's a np dot mean of the prices. Okay, and you can also do np dot median of the prices, and you can also do np dot standard deviation (STD) of the prices. Okay, and let's shift enter. Oh, it only gives you the last one. Okay, so let me just print those. Print those three things. Okay, so you can see that we got the same exact value for the mean value, and also for the standard deviation, we got the same exact value. Of course, it should be. And in addition to that, we got the median value. All right. Okay, so far it makes sense. So we got this. So let's assume that in Long Island in the year 2020, these are all the cars that are sold. So this is the population. That's how we're going to think of this data set. Okay, what's the length of the data set? So we have like 40,000 cars. Okay, so 40,000 cars is all the cars sold in a district in Long Island. That's a population, and let's say our goal is to find the mean value, the median, and the standard deviation of the population just by having some samples, okay? So now question, what size sample should we draw? Any ideas? Let's say we randomly tagged 10 cars, okay, from that district, okay, and then we looked at their price. Okay, so we're going to randomly select 10 of them. And the way we do that is by going to cars 2020, and there's a sample functionality. And n equals to 10 will give you a sample of 10 cars. 10 random cars are sampled. And then we can look at their price sold. And then we can now make this as a NumPy array. And we can designate this as the sample. So this is going to be my sample, okay? And then what we are going to do is we're going to print the three things. So np.mean of the sample, np.median of the sample, and np.standard deviation of the sample, okay? So let's see what they say. Okay, first of all, what happened to the mean? It's much less. the median is also much less, and then the standard deviation is much less. Okay, so the sample that we randomly selected kind of ended on the cheaper side. Okay, so let's do this again. Shift Enter. This time, what happened? The average went higher than this, right? And median also became higher. Of course, if the mean value goes higher, the median would also tend to become higher. And but somehow our standard deviation is smaller. Okay, standard deviation still became smaller. Yes.
Can we see which cars it took for the sample?
Because I already changed to NumPy array. Let's do this. If you want that, let's say sample cars equals to this, and then sample cars dot head. Oh no, just a minute. I shouldn't be doing that. I'm not just taking that column. So 10 random samples, and these are the cars that we just selected randomly. It's not the previous one, okay? And then we can now turn the sample as the NumPy array of sample cars of price sold. And then once you have that, you can do the same thing as before. You can print this, okay? So this time, again, the average is slightly above. Median is pretty close, I think. No, yeah, median is pretty close. The actual median is 6,050. Our median is 6,150. So that's pretty good, right? Okay, and then again, you can see that the sample value, sample standard deviation is smaller than the actual. The actual is quite bigger, right? And this will be something that you will observe that in many cases, it's often that the sample standard deviation is smaller, more frequently smaller than the actual population standard deviation because of that problem. What was it? Bessel correction. The sample standard deviation that we are having here is not Bessel corrected, so it's slightly below. Okay, so far so good. But how do we have a confidence interval? Well, so the way we are going to do confidence interval would be using something called the t-distribution. But here's a way to figure out the confidence interval. So what I'm going to do is, this is not practical because in most cases we don't have all the data. But if we want to have a confidence interval of the mean value of the population from the fact that we can do samples of 10, what you can do is you can take samples of 10 but repeat that 100 times and generate all these collection of mean values, collections of the median values, collections of the standard deviation values, and then just get their mean, okay? And then see how close they are. So here's what I'm going to do. List of means, okay? I'm going to generate a list of means, list of medians. Let me say list of means, list of medians, and list of standard deviations. Or let me do variances. Okay. So we're going to make these things, and I'm going to do a for loop so that I can sample sizes of 10 100 times, okay? So here's what I'm going to do. I'm going to take this one, copy it here, but I'm going to put it inside a for loop. So for I in range 100, so that whatever that's inside the for loop will be repeated 100 times. And every time I'm going to get a sample of 10 cars, and then I'm going to be appending these values to each of the sorry, let me just add one more. List Bessel corrected variance. Okay. Okay. So let's see. So list means will now be appended by the NP mean of the sample that we just chose. List medians will now be appended by the median of the sample that we just chose. And then list variances will now be appended by standard deviation of the sample squared, because we want variances, okay? And then list of the Bessel corrected variance is what you have to do. There are two ways to do this. Let's do the straightforward way, which is to add up all the values of the sample, but then you do sample minus the NP mean sample. So subtract the mean value, you take the square, right? And then you divide. What you're going to be doing is you're going to divide not by 10. See, n is 10, but instead we're going to divide by what? What do you think? Huh? 9, because we're dividing by n minus 1, okay? So we're going to do that. And let's execute this. Oh, sorry. I don't know why I said appended. Okay, append. All right. Okay, so done. So we did this, and now let's look at the means. Dot sorted. Oh, list of means. Sorry. List means. Okay. We're going to sort this from the least to the max. Okay. And then let's look at list means. So we see that the least value of the average is 4231. Maximum value of the average is 17. That's quite high. But let's look at this. We have hundreds of these samples of 10, right? So what's the 90%? That will be like taking 5 cars away from the left and 5 cars away from the right, right? So we can say that if we look at this list of means, and you go from 5 colon and negative 5, then we get 4799 to 13201, okay? And with 90% confidence, we can say that the actual population mean is in this confidence interval. It's kind of stupid because it's just so large, okay? We can actually do better with t-distribution, okay? That's something that we'll see, okay? So that's the beauty of mathematics. But this is like one way to figure out confidence interval. All right. Now, let's see what the mean value of the list of means is. So if I do np.mean of list means, we get 8582. That's actually larger than, what was our actual, oh. So if I compare, that is actually quite good, okay. All right, that's pretty good, right? The mean of means is quite close to the actual mean. That's good. How about the np.mean of the list medians? 6218, not bad. That's pretty good, right? And then NP dot mean of, sorry, I need this squared so I can compare with the variance. So list variances. Did I have variance or variances? Variances, okay. Variances. And as you can see, what happened? This is quite off, right? It's very off, actually. Don't you see? Yeah. But instead, if we use the Bessel corrected one, what can we say? If we use the Bessel corrected variance, it's still somewhat, and the problem is that the data set that we have is highly skewed, so it kind of underperforms in that case. But still, you see that the Bessel corrected one is much better, much closer to the actual population variance than the non-Bessel corrected one. There's a huge difference, right? So that's the reason why we use Bessel correction. So anytime you see the formula for the variance and there's something, there's like n minus 1 in the denominator, then you would then you would know that, oh, that's the Bessel corrected one. It's a way to fix this problem of constantly having underestimating the variance. Okay. Okay. Any questions? All right. So your first